Have you ever wondered how scientists can identify the different chemicals present in perfume, food flavoring, or even a blood sample? One of the most effective techniques used to separate and identify the compounds is gas chromatography, or GC. Today, I will introduce the basic principle, working mechanism, and applications of gas chromatography. Gas chromatography, or GC, is an analytical technique used to separate the components of a mixture. In this technique, the sample is dissolved in a solvent, vaporized, and separated based on its distribution between two phases. The first one is the stationary phase, and the second one is the mobile phase. The mobile phase, also known as the carrier gas, is an inert gas that transports the vaporized sample through a heated column. Gas chromatography can be classified into two main types: gas-liquid chromatography, where the stationary phase is a liquid coated on a solid support, and the second one is a gas-solid chromatography, where the stationary phase is a solid material. In both types, the mobile phase is a gas. The principle of gas chromatography begins when the sample is injected into the inlet and vaporized. The carrier gas then moves the sample through the column. As each component interacts differently with the stationary phase, they are travel at different speed and become separated. Finally, each compound reaches the detector, which records the signals electronically. Due to its accuracy and sensitivity, gas chromatography is widely used in environmental monitoring, petroleum industry, chemical analysis, food quality control, and pharmaceutical research. Next, the main purpose of this presentation is to provide a clear understanding of gas chromatography. Specifically, this presentation aims to determine the retention times of N-butanol and 2-propanol. The second one is to identify the components present in the standard mixture based on the TR. The third one is to identify the components present in an unknown sample. The last one is to determine the effect of temperature on TR and RS.
First of all, we have a procedure. As you can see, this is a picture of the flow gas chromatography. The first one, we go through the carrier gas. The number two, we go through the pressure regulator or flow controller. And then we go to injected sample inlet. And then we go to GC column. And number 5, we go through the ovens. After that, we go through the detected flame ionization detected, FID. And the last one, we go through the data system, or we can call computer, for data analysis. Next slide, we have a function of flow gas chromatography. The first one, we have a carrier gas cylinder, supplier of inert gas, helium or nitrogen, action as the mobile phase to carry the sample through the column. And then the number 2, we have a pressure regulator or flow controller, control the pressure and flow rates of the carrier gas and ensure the stable and consistent gas flow. Number 3, we have injected sample inlet, introduce the liquid sample into the GC, vaporizes the sample before entering the column. The number 4, we have a GC column, contains the stationary phase, responsible for separating compounds based on volatility and interaction. Number 5, we have oven, house the GC column, control the column temperature to the affect retention time and separation. And number 6, we have a detector, flame ionization detector, FID, detect compounds as they exit the columns and then convert them into electrical signal. And the last one, we have a data system, or we can calling the computer, record detector signals and display chromatography for analysis.
Now, I'll present the gas chromatography results obtained from our experiment. At 70 degrees Celsius, the standard mixture produced two peaks with retention times of approximately 2.67 minutes and 5.81 minutes. To identify these peaks, we compared them with the individual standards. The 2-propanol standard had a retention time of about 2.71 minutes, while N-butanol appeared at around 5.96 minutes. For the unknown sample at the same temperature, the chromatogram also showed two peaks at approximately 2.65 minutes and 5.96 minutes. These values are very close to the retention time of the two standards, indicating that the unknown sample contains both 2-propanol and N-butanol. We also investigated the effect of column temperature on retention time using the standard mixture. When the temperature was increased from 70 degrees Celsius to 100 degrees Celsius, the retention time decreased from 2.67 and 5.81 minutes to about 2.27 and 3.28 minutes. At 140 degrees Celsius, they decrease even further to approximately 1.96 minutes and 2.24 minutes. This shows that increasing the column temperature reduces the retention time because the compounds become more volatile and spend less time interacting with the stationary phase. As a result, they travel through the column faster and elute earlier. Overall, our gas chromatography results successfully identified the unknown sample as a mixture of 2-propanol and N-butanol, while also demonstrating the effect of temperature on chromatographic separation.
Moving on to the discussion of this experiment. Gas chromatography is widely used mainly to identify the unknown compound in the sample by comparing their result with known sample. But how is that happen? By matching their peaks of the known sample in this experiment we use is N-butanol and 3-propanol and their retention time. This experiment observed that temperature also can change the rate of reaction of this experiment. Why? How it does happen? Because we can see that at 140 degrees Celsius, the substance move via instrument faster rather than at 70 degree Celsius. Why? Because due to the higher temperature, the chemical can convert it into gas much quickly. In other words, less time needed for the materials to stick inside the instrument. But we cannot apply the higher temperature from 140 degree because the gas will be moved via instrument too fast. So what happened? So that in result, the instrument might not be able to separate them properly.
And the last one, we have a conclusion. In conclusion, gas chromatography was successfully used to separate and identify propanol and butanol. The compound in the unknown sample were identified by comparing their retention times with two of the standard measure. The experiment demonstrates the column temperature plays an important role in controlling retention time and peak resolution. Overall, the objective of the experiment was successful achieved and gas chromatography proved to be an effective technique for the analysis of volatile organic compounds.